Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. So this is May, and we start May with the presentation of Professor Laura Palagi. We are very pleased to have her here today. She's a full professor at the Sapienza University at the Department of Computer Control and Management Engineering. So Laura has her main area is continuous optimization, and she has done work in semi-definite programming, in mixed nonlinear programming, continuous nonlinear programming of problems. She has worked for a long time on supervector machines. This is a work that we all working on supervector machines know very well. And just to mention a few of her achievements, in 2020, last year, she received a Best Paper Award at the Journal of Global Optimization. She has published in leading journals in the field, such as Mathematical Programming, Mathematics of OR, European Journal of Operations Research, but also journals from fields of energy and other fields of applications. So we are very pleased to have today Laura with us, and the floor is yours. And for the questions, remember that if you have a very, very urgent question, you can put it in the chat and I will read it. And otherwise, we have plenty of time at the end for a Q&A session. Thank you so much.
Thank you, Dolores. Thank you for the kind invitation. It's a pleasure for me to stay here for speaking in this very nice series, really a nice, strong effort, but very nice, interesting stuff. So what I'm going to present today is a joint paper with Ruggiero Seccia, which was a PhD student. And it's about block and sample decomposition in deep network training. Actually, the general problem that we are discussing will be more general than deep network, but the deep network was that motivates our effort, our study, and also all the numerical results are on deep networks. So this was the reason for this. So just for put some framework very quickly, I will focus on supervised regression problems. So I assume that I have a target set given by features, vectors, x, and labels, which are y, with values in the reals. And what we want to define is considering a class of special machine learning models, which are those coming from feedforward neural network, which will be parameterized with some omega. And what learning means is estimating both the function and the parameters in a way that they return values as close as possible to the target value that is known here. So actually, it is a long, we can speak a lot about which is the strategy in learning. However, let's focus on our feedforward deep neural network just to fix the idea which are the parameters here, which kind of function we are defining. So in feedforward deep neural network, we have that the units are the artificial neurons, which are actually some linear combination of the inputs with at which are applied some activation function that can take any standard form, so sigmoidal function with linear units, whatever you want. And these artificial neurons are organized into layers. And these layers have no loops, without loops, and so it's a one-way connection from the input to the output. Here is a picture, and here I'm assuming only one output, but just for sake of simplicity, the gray and black are what we call the hidden layers, which are the parameters involved in this kind of function. We have the number of layers, how many layers, hidden layers do we have, and how many neurons we have in the layers. Then we have also other parameters which are tied to the activation function. I don't even mention about this. And then the most important, some other important, let's say, are the weights over the arcs here. So I will denote the weights with a capital W here. W1 means all the weights here for the first layer that goes from the input to the first layer, and so on. W2 and W3 in this case. Okay, so what learning means? We need to find, we need to have some performance measure. As usual, I don't want to enter too much details. What we are going to use here is the regularized empirical risk minimization principle. So we use some surrogate measure of the true function that we want to minimize, which is the expected risk, the expected value of the error that we are doing on unseen data that are coming after the training. And the regularized empirical risk is based instead of on the use of a function, which is the empirical risk, which is instead measuring the error over the data that are available, and added some kind of regularized term, which in some sense penalizes the complexity of the machine. So the class of function f that we are using is that one coming from feedforward neural networks. So the output, assume that the last layer is linear, so we don't have a g applied to the last artificial neuron, will have this kind of structure. So we start from the input, we multiply by our weights, we then apply the activation function that can be different. I will assume that's the same here for all the layers, does not matter, and it's not important in this framework, and so on and so forth until the last layer. And the type of loss function that I'm using for measuring the distance between the predicted output and the true output here is the quadratic square loss, which is the standard, one of the most used function in this framework. And I will use some kind of ridge regularization, so square norm of the weights here, or the parameters. So the problem that we are actually our target general problem is this one, in which we want to fix both the f. So the f has this form, but we will see in a while that to define this form, we need to fix some called hyperparameters. So this omega here represents the parameter of our problem, and actually among these parameters we can distinguish among hyperparameters, and I will say, for sake of simplicity, I will just mention the layer and the number of neurons in the layer for the network. And then there are others which are called parameters, which are the weights, the W, on the weights on the arc of the networks. And once we have fixed the layer and the neurons, we have specified the topology of our network. And when we fix the weights, we are choosing among this topology a specific network. So in principle, what you want to do is a joint selection of the weights and the hyperparameters. This is difficult. I will not enter details. So usually there is an heuristic choice for the hyperparameters that can be grid search, random search, whatever, and then some kind of optimal choice for the weights. I put the optimal here in brackets because we will see that optimal is not exact. We will try to choose the W by solving an optimization problem, which is saying that we optimal solution. Then thus at the end, the problem that we are addressing here is what we call the weights optimization problem. So forget about the pi that will be fixed outside our problem to a given value, then our problem will be choose the weights, only the weights. So minimizing this function here. What about this function? Okay, I will write down in this form because I want to stress two things about this function. The first one is that this is a finite sum of function of small errors on each single data. So this function sum is up to capital P, which are the number of samples. And also that the variable has some special meaning because these are weights of layers.
Laura?
Yeah?
I'm not sure that we see your slides. Could it be that maybe something is wrong with the sharing at the moment?
Because I see myself on the other screen, so I don't know what. Don't you see anything?
I don't.
Yes, slide number 5.
I can't see it myself. I see it very clear.
Okay, then it's my problem.
You have to refresh it, then we'll be fine.
Okay, yeah, apologies.
Okay, so can I
she
continue?
can restart her machine again.
Sorry?
And if
She
you can go ahead.
reboot the
Yeah.
problem. The problem will appear if she restart the machine, maybe.
Yes, yes. It's only me. Sorry, apologies for the interruption.
It's only 2 Dolores, so I can continue.
Yes, you can.
Okay.
You can.
Okay, that's fine. Okay, so this is a finite sum repeated, and I also stress the fact that the weights are the variables, the weights, and the weights are divided into layers. This is something that I'm going to exploit both these two aspects. This is the reason why I want to stress from the beginning. So this is an unconstrained problem, highly not convex, highly nonlinear. Actually, there are a lot of local minimizer, a lot of stationary points. And what we can expect it to do is to find at least some point that satisfies at least the first optimality condition, which is the gradient of the function being 0. If you are going to use some more complicated algorithm involving second order condition, then you may even expect to have second order stuff, but usually you're not. But what is interesting is that this will be a finite sum with a large number of variables, and the training about the requirement about training make this kind of problem special one, because you might need to solve a lot of this problem of this form, because you need to set up the hyperparameters. And also within the hyperparameter setting, you have usually what is called the k-fold cross-validation. So usually you need to solve a lot of these problems to train your network. So you need to be fast. Second, you don't need to go below the statistical error, because we are training a machine to predict something that is coming to predict something that is not seen. So we don't want to learn very well what we already know, but we want to learn how to predict well new unseen data. So, and this is done by some tricks, such as, for example, iris stopping in this kind of context. And then in general, so what you want is to prefer algorithm that can reach a given accuracy quite fast, and rather than having high accuracy but take longer. And this is something that motivates most of the research for solving this problem in the literature in the last, let's say, 20 years almost, but more or less. Okay, let's discuss a little bit about this aspect, non-convexity of the problem. So from the non-convex point of the non-convexity is not so important from the statistical point of view, because usually what is claimed, I'm not sure that it's always true, but there are some results on this, so it's true for some cases, that you will have a lot of local minimizer and saddle point that have very good generalization properties. So you don't need to go to truly find the global solution. From the optimization point of view, the true difficult stays in the plateau, because this function, this is the shape of a function in 2 dimensions obtained by a 2-layer function fixing all the others. You have this plateau, so this region where the function is flat, and then there is sudden some hill here. And if you end up in some of these places, you will be very slow. And further convexity instead is a strong assumption used in most of the algorithms that exploit the summation, the sum, let's call the sample decomposition for proving convergence of the method. Okay. So, however, for the time being, I'm not too much, don't care too much about convexity, because I'm only interested in finding the stationary point. And at most, what I can do is using some very basic multi-step procedure to improve the solution if I need. We will do this in the numerical results to show what happens in this case. So now the issue is more large scale, and large scale means here it's declined in 2 ways, because we have both the big data and the deep network. Big data means huge number of samples, so this summation will be very long. And deep means that you have a lot of layers and many neurons for each layers. And so this means that your weights will be a large vector with D. So our aim was to try to exploit both these two aspects to improve the performance of, let's say, called standard and constraint method. And to see what standard means, I will start with the basic method that has been defined at the earlier I90s for this kind of problem, which is what is called the vanilla gradient. And the vanilla gradient is neither more than the gradient method with a constant step size that is usually called the learning rate. But however, we can define the gradient method as usual, and this step size should be chosen properly in some way, either a search, constant, diminishing step size. We know that it can be proved that this method converges. This was called backpropagation because the way of evaluating the gradient in a deep network requires some trick that we are going to exploit it later, just want to mention. What are the characteristics of this method? In this method, we are updating, we are using all the sample at the time because the gradient is the full gradient. It's also called batch gradient. And we are not have any sparsity partner because we are updating all the weights at the time. So we are going to have both all the sample and all the variable involved in the update of the iteration. So this means that the cost of the iteration depends both on P and D. So which is the goal here? The goal is to try to reduce the computational cost per iteration, not only here, but in all the literature that we know. And actually, we'll put first sample-wise decomposition, that is, don't use the full gradient, but use only mini batch method. So, for example, incremental gradient, stochastic gradient, all the variants that have been proposed in these frameworks are in this framework fall in this case. So, sample decomposition, exploited the summation. But there is also another way to exploit the computational cost, which is block variable decomposition. So instead of updating the full vector W, update in a sparse way. And what we are going to propose here is to use a special update of the W that exploits the layer structure of the network. So I'll call it Blackboard block layer decomposition. You will be in a while what does it mean. And then we are going to join these two in, so the block decomposition with the sample decomposition in a new method, which is called BLINK, block layer incremental gradient. Okay, let's start. So since the sample-wise decomposition is well known for everybody, we'll go there very shortly at the end. I will start with the block variable decomposition. That is also something known, but not so well applied in the fields of machine learning neural networks. So here I'm forgetting about the additive form of the function, and only I will focus on the variable. So what does it mean that I want to have a sparse update of the weights? This means that I'm going to choose among all the variables that are numbered from 1 to D, some block, capital B, and I'm updating only those variables which are within the block. So the new variable will be exactly equal to the one before if the variable is not selected to be updated, or I will use a gradient type updating here if instead the variable is in the block. So this is a very general framework. And actually, if the block is the full set of variable, this is the batch gradient. If instead you are taking just one coordinate, one variable at a time, you have what is called the coordinate descent method, but you can stay in the middle and have what it's called block coordinate. Now, block coordinates is a very well-known method, so we only need to understand here how to apply in a clever way to the deep neural network. What are the reasons to apply such kind of method? First of all, because fixing some of the variable, you can find some special structure in the remaining one that can be exploited. Second, you are going to solve smaller problems. You need to solve more than one, but you are going to solve smaller problems. You can, this might speed up the decrease of your error, and so you might activate some early stop procedure avoiding to reach the minimum, so stopping the optimization area, you might escape from the attraction of some local minimizer, and you can use distributed parallel optimization. I will try to show you at least the last four parts. We have not used distributed optimization. So let's see why we think that exploiting a block decomposition is useful for deep network. The first stuff is that the network has a natural decomposition, because we have that the weights appears in a different section of your objective function. So you have the W, the weights of the first layer, just multiply the input and appears here. Then you have this layer, the layer that propagates, the weights of the layer that propagates as until the last one, WL. So our proposal was, okay, let's think about a decomposition along the layers. So instead of taking variables randomly or with any rule, our rule will be that of looking to the layers. There is some other reason that will be clear in a while. So now what we are doing is, instead of selecting just group of variables, different group of variables, we select layers of variables. So W with this apex J means that we are selecting the J layer, and we are updating if we have selected it or not. So what are the key aspects here? So how many and which layers we have to select at each step in order to obtain convergence, obtain some special structure of the subproblem, and save the computation, because these are our three aims. So let's see first on a simple example, which is not due to us, but was already proposed by Grip and some other, for what is called a shallow network. So whenever you have just one layer. So when you have just one layer, here is, I call the weights like W and V, just to understand what's going on. And if you look to the objective function, it's clear that whenever you fix the V, you have that this part is fixed. So what you have here is a linear, strongly convex, linearly square problem. So optimizing with respect to the V, when the W is fixed, it's quite easy. You can find a global solution. Okay, so in this framework, it's been presented two kind of approaches. The first one was extreme learning, that was select randomly the W. Sorry, I'm distracted by the fact that I see that there is something not working, but I hope it's not me. You will tell me. Okay, so if you can fix randomly the W and then solve with respect to the V, this globally solve, and then keeping randomly this W, you will find something, you will find a network here. This seems to be, of course, you will not even find the stationary point of your error function here. Or you can alternate the minimization between the W and the V, so the V can be solved in to the global optimality. About the W, you need to have some trick because it's not convex, but we will arrive to this in a while. Then you alternate this, and if you can prove convergence, this will arrive to a stationary point of your function. So our idea was trying to extend this approach of shallow network to network. So first of all, let us discuss two blocks which are quite special decomposition method, because it can be proved. And this is a generalization of results given by Grip and Chandrone that improves a Gauss-Seidel method. This is why I call this GS squared. So the two block decomposition converge when you solve to global optimality one of the two problems, so the one that we can solve, so with respect to V, and for the other one, you are using any descent algorithm that returns a stationary point, or even less, you can do only few iterations of this kind of descent algorithm. So you can alternate optimal minimization of the V and some few iteration of a descent algorithm that used gradient in some way. And in this, I will not be too much details on this, but in these ways you can prove convergence. So the idea is, okay, let's try to use for deep networks. So also for deep network, we can see similar structure, because when we fix When you're going to fix the layer, the hidden layer, and the only one that is not fixed is the last one, the W4 here in this case, then we have again a linearly squared problem, strongly convex. So if we divide it into two blocks, one is the last layer and the other one is all the others, then we can still apply the convergence results. What's the problem here? That when we have to discuss about deep network, we want to save computation. And now the computation is due to the fact that you need to evaluate the objective function and the gradient with respect to W. And this implies, is well known, that you have to make a forward and forward propagation on the input and backward propagation of the error to obtain the full gradient. Now, what happens if you are updating only some weights? So when you are updating, for example, the last weights, the W4, then you can save all the computation up to the last hidden layer, and then to update to evaluate the error and the gradient, you only need to forward and backward propagation for this layer only. But when you're going to update all the others, then you need to go back and up for all the layers. So you are not saving too much computation making these two steps, because you are alternating an easy one with a very difficult evaluation here. So the idea is trying to do more than two blocks to exploit better this situation here. And if you're going to exploit more than two blocks, you need to take care, because the Gauss-Seidel, pure Gauss-Seidel, requires that you optimize to global optimality with respect to the block. So we need to apply something different, which again, it's not our contribution, but is given, again, it's an old paper by Grippo and Cendrone. And here there is something. So you can have convergence of the composition method with more than two blocks if you pay something in the iteration. And what you need to pay is essentially to make a line search procedure along the block that you are using, and to enforce the fact that the distance among two iterates is going to zero, so some kind of, I would call it, proximal point condition. And for this, this has been exploited again in shallow network to define decomposition, which are different from those that I discussed before, that allows more than two blocks. So now what happens when we go to deep network? So when we go to deep network, we need again to take care about the choice of the layer. So we try different possibility for this, because there is a rule that I forgot to mention, that everything works if the layer, if the decomposition, the blocks in the decomposition are chosen, let's say, periodically within a finite number of iterations. So we decide to have some kind of iterative stuff over the blocks layers so that we don't care about this. But the way you select the layer, it has an impact on the way the computational cost of evaluating every time the gradient and even the objective function. Remember that you need to have line search. So this was the problem, and we want, as a first step, we check whether this works, really allows to improve with respect to a standard method that update the variable altogether. So the first step was trying to see what happens between a standard unconstrained method that is updating all the variable at the time and some block variable decomposition. And we use LBFGS as a comparison. And we decide at the end, it's the only one that I'm going to present, that the best way is what we call the backward selection. So starting updating the weights of the layers from the last one up to the first one. Okay, so I will going to show some results. Just want to mention that you are paying something. So the iteration of the single block decomposition is heavier than using just the gradient with a constant subsides, for example, as in the back propagation, because you need to have a line search. And line search costs because you need to evaluate the function. at least once, so once more than needed. So our first idea was try to understand if this computational price that we are paying is worthwhile, so if we can really improve something. And actually the answer is yes. I'm going to show this. So there is the first set of problems here. It's 7 problems. Here I don't enter details. So the only thing that I want to mention that we tried 5 different types of networks. And what is changing in this network is the number of layers and number of neurons per layer. Actually, mostly the number of layers. So the first one is a shallow network, or the other a deep network with different number of neurons per layer. So here we can use 2 stopping criteria, actually, which are 3 stopping criteria, because this is a standard unconstrained method. So we are using the gradient, we are evaluating the gradient at each iteration, so we can check if we are going down the norm of the gradient. We can check also if the objective function is not improving enough between 2 iterations. And then we also have a time limit, because I just remember that we want to have something that is going to reach good accuracy in a short time. So we don't want to go up to the end of the optimization. And just to understand what's going on, we also try to have a multi-start run on each problem. So here, the hyperparameters are fixed altogether to some values. We look to the best value for the problem, but these are independent from the method, and then we use the same hyperparameter for all the problems. So it's just the weight optimization with the same hyperparameter and just 10 multi-start from random point. And what I'm going to report are the best value over this multi-start run and the average. Not the train, I wrote the train for short, but actually the objective function and the test error, which is something that also important when we are solving machine learning problems. Okay, so the first one is here. So this first one is our backward block layer decomposition versus LBFGS. And I'm reporting the wins, the loose and the ties, being ties within the 5% of the value. So what we see is that increasing the dimension, the composition seems to be better. So the objective function that we can find is actually better. And also, this is in general better also on the test error. So this is not always true that having a better objective function produce overfitting. In some cases it is, but less cases than it gives better value. And also what I want to mention here is that we also report the running time, because there is this 150-second maximum computational time, but the algorithm can stop earlier. And actually, we see here that, for example, in the last one, where we find always a better objective function value, we always took more time than the LBFGS. But I will show in a while what happens when in the very early seconds part of the optimization, which is what is important. Okay, the other one was an average test, because it may happen that this best run is a best run, and then on the others, more or less, they are the same, or we are not going so well. And actually, so what we do is a 2-tailed t-test with a threshold for the p-value, which is 0.05. And so we are going to report the average test error, the win over the average test error. So here you see that actually things are going quite good, and in general, they are statistically different. So there are only a few problems, a few cases where you cannot say that there is statistical difference. So it seems that the block layer decomposition outperforms the full optimization, in particular when the dimension of the layer increases, which is what we are expected, because we are exploiting the layer, the depth of our network. Okay, so now let's see what happens for, sorry, I forgot. This was what I was mentioning. These are some graphs over the first 30-second runs on some of the problems, of course, because they are 38. We just take took the cases that appears most frequently. So, and just to have understand what's going on. So we see that we have the yellow one that it seems that goes down always quickly rather than the LBFGS, and this is almost the case. And in some cases, it seems that the LBFGS remain trapped or in some region where it's going really slow. And instead, we are able to improve the solution. Okay, so, and remember that we want to reach accuracy in few seconds, because you might activate iris stopping, which is not here, of course, because we want to understand what's the optimization point of view, not only the machine learning point of view. Okay, so that's about the block. What about the sample decomposition? So now let's forget about the W and take care about only the summation. This is something that has been done a lot. I don't want to spend too much time. Just say that here you need to have the step size that is going to 0, because the direction that you're using, essentially the direction that you're using and the objective function are not consistent. So if you want to enforce convergence, you need to pay something, and what you pay here is driving the step size to 0 that slow down the iteration in general. It's a tricky part, this one, how to make this step size going to 0 not too fast. There is an impressive number of papers that define some variants of the incremental gradient, stochastic gradient. There is a very nice survey which appears in 4 years ago, perhaps from Buteau, Curtis, and Nosda. I will not enter too many details, because what I want to understand now is if I can exploit this structure within my block decomposition. So, and actually, so to define our Blink algorithm, so a block gradient, block layer, which is also an incremental gradient. So what does it mean? It means that we want to select a mini batch, so some of the sample that makes the summation, and works with this sample over the block. So we start selecting some sample, then we update our weights. Forget about this cyclically. We update our weights of the layer. We are always discussing about layer decomposition. Only with this small sample of with small batch of samples. So what does it mean? That when I'm updating my layer W, I'm not using the full. Not only I'm using a sparse update on the W, but I'm also using only a portion of my sample here. So this is not the full gradient with respect to the WJ. It's only some pieces. Actually, the framework is more general than, rather than deep network. The convergence can be proved just considering finite summation and block decomposition. But I mean, here I'm going to present only this. So now the trick is, can we prove convergence in this case? Because we can prove convergence using line search in the block decomposition. In this case, we are using also some mini batch of the error, so we are expecting that we can prove convergence with the step size that is going to 0 again. And actually we can, and I will not report the detail, which are really tricky, but essentially we are following the same approach that is done in Versekas when he is using, is proving convergence of gradient method with error. So we prove that this method block the composition with incremental gradient, so mini batch on the gradient is fit in this framework gradient with errors, and we prove that the errors is going to 0 when the step size is going to 0. And so we can prove convergence in this framework. And now the thing is, how do we select the mini batch and how do we select the blocks in a way that the convergence works and the computation is saved? Laura? So for the, yes?
Yes.
10 minutes. Yes, we have done. Okay.
Yes.
So for the blocks, we will use again the backward selection that we have done for the block decomposition, and instead for the selection of the mini batch, we applied an incremental mini batch. So I will go at the end to this. So it's an incremental, we are just deciding the order of the sample or the mini batch, and we are using this every time, always the same. So now what's going on? What happens? Let's see. We try again on the data set that we have before, plus we add some 3 more larger, very large set, because we want to exploit here also the fact that we have a lot of samples and the other problems are not so big. So the structure of the network is the same as before, but we have these 3 problems that are much larger. Also, we need to say that, of course, there exists a lot of implementation of the incremental gradient, very, very efficient implementation of the incremental gradient, that, however, use some tricky stuff that we don't want to use within our framework at the very beginning, because we want to have the simple stuff to be compared with, to understand if the approach was promising. So if we really can improve with respect to a very basic situation. And also, I will not report any other details results on this, but then we also test some more complicated mini batch method rather than incremental gradient, and still it works very well. The block implementation together with the sample implementation works very well. Again, we have 10 multi-started run, and now the only thing that is going to change is the stopping criteria, because in incremental gradient you never evaluate the objective function nor the full gradient, so we cannot use this for the stopping criterion. We have only a CPU time limit of 60 seconds. Okay, let's see what happens. Again, as before, I will show you the best results over the 10 runs. And here we have 10 problems instead of 7. And again, we can see that actually about the objective function, our Bling method seems to win to respect to an incremental gradient, fair with our incremental gradient implementation here, and lose almost never, and just on the first network. And also it's also better on the test error here. And also on average, things are a little bit more complicated, because actually we cannot compare, we are not statistically different on a lot of instances in a small network, but if you look to the largest one, we have only 3 problems that cannot be compared from the statistical point of view, and all the other 7 we are going to win. And in general, on those that we can compare with, we are going to win. So this is the average test error. So again, it seems to be quite effective. And also what is interesting, okay, yes, sorry, this is quite small. You only have to look to the red stuff. So the red means better. And the first column is our algorithm, the second column is incremental gradient, and objective function and test error. And here we have 3 networks with increasing depth. So from 1, 5, and 10, all with 50 neurons. And we see here that in the last one, it seems to be much better, both in the objective function obtained and in the test error obtained. So increasing the dimension of the problem seems to increase the performance of the method itself. Also, what is interesting here is the behavior over this. These are 10 seconds of run, and these are again the most common behavior that we have. So we see that in general we are more or less all either comparable or a little bit faster in going down. And what's also happened is that we have less spike. So the incremental gradient is also called a crazy method, because of course oscillated a lot before you find you reduce the step size in a correct way. So actually we may see this spike over there. And also, for example, there are some problems which we see that we are going to escape from local area, bad area, let's say faster rather than the standard incremental method. We also check Okay, this is also the last check, almost 2 slides. Also try to understand how much the depth of the network influences the performance of the algorithm. And what we did is, let's say, some naive comparison, taking the network with the shallow network with 50 neurons and the larger network with 50 neurons for each layer. And then we make the ratio between the best value find in the 2 networks. So when this is 1, this means that we find the same value. Greater than 1 means that we are going worst, and less than 1, so that the depth is making things worse, and less than 1, that the depth is things make better. So, and if you see what is affected more for the depth seems to be the incremental gradient. Here, red is worst. So being red is worse rather than being black. Very last, we want also to understand if this improvement were due only to the block decomposition or to the block and sample decomposition. And this depends. I'm reporting here only 2 network again, the small one and the larger one. And actually here you see that it's not only the block decomposition that counts for, of course, for a small network, shallow network, block decomposition plays an important role, but you see here what this last problem where you have a lot of sample, again, the blink seems to be more important. And when you increase the dimension, surprisingly enough, this affects also the problem with less sample here. Okay, and this is the time. Okay, let's conclude this. So what we have proposed is a joint use of mini-batch approach with the decomposition technique on the variable. This allows us to speed up with respect to standard, both on the side of the full non-sparsity, so full update of the weights, on the other side from the full batch method. And then there is also, from the machine learning viewpoint, seems to go faster at the very beginning, which is something which is appreciated in general. And among the future works, there is the fact of lightening the assumptions that are used for proving convergence, because the theory of gradient with errors requires strong assumption. There is no convexity, but there are strong assumptions on the objective function that may not be satisfied by deep neural network. Okay, here is the references, and thank you again for your attention, and again the organizing for this nice series. And I'm done, ready for the question.
Thank you so much, Laura, for keeping to the time and for the very, very interesting topic on deep networks. So we open the floor for questions. So remember that you can unmute. Maybe you can also show your video and pose your question. So yes, so Mehidin, would you like to unmute and ask your question? Otherwise, you can post it on your on the chat.
Okay, now you hear me, I think?
Yes, we can hear you very well.
Oh, hi, Laura. Okay, thank you for the interesting talk. Just I have noticed, I have mentioned about the LBFGS method that the time is less than the other method. I think B square LD or something like this. So have you tried to increase the number of storage, I mean the storage vectors for LBFGS, just to see what is going on? Is it going to be
we did. I mean, of course, I did not report everything. I did not say also a lot of things. So now we use this. Of course, we try to we try to put the setting of the LBFGS in the best way possible for the LBFGS, but then there is also some trade-off, because I mention it very quickly. We itself use the LBFGS within our block decomposition, because to prove convergence, where is it here? To prove convergence, when we have the block decomposition, we need to enforce these properties that with respect to some kind of line search with respect to the block, and then some kind of proximal point condition. And so to be fair, to be sure that we are not implementing something quite good or quite bad in our unconstrained part for the block decomposition, we use also there the LBFGS. So we try to find a trade-off in a way that we don't need to have different setting for the general unconstrained problem, full unconstrained problem, and the sub-problems, because otherwise, of course, we can, then it will be not completely fair, the comparison. But we did it. And so we increment the memory. Now I think that the results here are, I'm not sure that it's 10. I can check it on the paper. It's on the paper nevertheless, but we also try to improve it, and there is still the difference. So because what we want to show here is not that LBFGS is faster than some other unconstrained method, but which is the impact of having a block decomposition with respect to the full decomposition. Okay, did I answer?
Fine. Okay, thank you. I'm really glad to hear this. Thank you, because
okay, thank you.
Thank you.
Thank you to you.
Thank you very much. Are there any other questions from the audience? Remember that you can either unmute or you can put your questions in the chat. Laura, you had the reach regression, the reach regularization.
Yeah.
Have you tried other regularizations?
No, this we didn't try actually, because we were focused on the fact that we want to understand the role of the block and the sample decomposition. So having the ridge regularization help us to have some property of the optimization problem, because in that case we are sure that global solution exists, so we don't care about compactness of the level set and so on and so forth. We didn't try other regularization actually.
Yeah, but it's only for
if we try, it was just for a joke, and I don't remember what happened. So it may perhaps we even try it, but not because we want to really understand what's going on for the method. We just try because this has an impact. I think has an impact on the optimization problem, of course, but mainly from the machine learning point of view.
Thank you. Emmanuel, you have a question?
Yes. Thank you, Laura, for this very clear and interesting talk. So I was wondering about the activation function you used then in your experiments. You said,
oh yeah, I forgot to mention it was
a problem in theory, but for the implementation it would probably be an interesting
feature. I forgot to mention here it was a sigmoid, and I think it was the Gaussian one. I can check it because I don't remember. It was, however, it was a sigmoid.
Not ReLU, not piecewise.
No, not ReLU, not at all. Yeah, not ReLU.
Thank you. Thank you. And do you have do you have an explanation why this 3-layer network with the endogenous node density is behaving differently?
Depends on, I think that this, you mean this one, 250, 200? Yes. I think that
so
depends on the
middle
number
layer
of
is
variables.
very thin.
Yeah, but this was, we want to try this because this is something that happens in convolutional network that have thin layer in the middle, so large and thin and large. And I think that one of the explanation is the number of variables. If you see here, I cannot see too much, but you see that actually there are, in this case, these are the larger number of variables here is in this network. So
yeah, but not dramatically, is it?
Okay, depends what do you mean by dramatically. So with respect to 3,000, 10,000 more.
No, wait.
Not dramatically more than this. No, I don't have I don't have an explanation. Actually, I want to look also to this because it's something that I want to exploit the fact that you have a lot of neurons. So because these are, of course, you're going to change something different. But I mean, we can check. I don't know. If you see here from the point of view of the test error, there is not a big difference actually.
Yes.
Because we win. So in the block decomposition, we can check what happens also with the other. But so it seems that it's not dramatically different from this other one, which is really big. But I mean, it's different. I don't have an explanation from the machine learning point of view. No. Unfortunately,
no, but you showed
from our point of view, there is a difference because here we have only three blocks of layers, plus and 2. Here we have 10. So here we are updating 10 times the blocks 10 times in a different way, 10 times. And here you are updating to have. So in order to update all the vectors, you are just using 3 blocks. Here you are using 10. So from the optimization point of view, this can make a difference, of course. But I cannot, so I've not studied into detail this aspect, I should be honest.
Because in one of the later transparencies, you had the significance test, and then it turned out that was the only one where there really was a striking similarity.
Yeah, it's true. It's true. Where is it? Here.
I was wondering that the topology of the network is having a large well, actually no. Actually, it's the same. Is it this one?
So actually, in this case, for this case here, when in the comparison with the blink, when there is both the block and the incremental gradient, statistical difference over the 10 stuff is not so significant for all the problems. So here we have the first network. Okay, we have all the problem with the p lower than 0.05, but here this in the middle we have a lot of. Remember that the problem are 10. So here actually a few of the problem are significantly different, and is the only one that I'm reporting here on the left, because for the other one does not mean making wins or ties or losing does not means anything. So in this last one, which is the deep one, we have more. I don't know. Here, perhaps you mean here. In the best run, this seems to be, but I mean, still, it's 6 to 4, 8 to 2. It's not significantly different from this larger.
I'm sorry. I probably had or have a weak memory on this. It was one of the last significant. So for
this one, significant, we have only 2. Here is.
Yes. No. That was mistaken. Sorry. So.
Okay.
But sorry for the confusion. But
don't worry.
I'm still interested in the one of the last ones where you compared tenfold more layers. I think that. With
one of the last when I compare what? Sorry, Manuel, I didn't catch.
Yes, can you go to the very end with the last table?
Okay, let's see.
Table. Yes, this one. You have
this is not okay. This is, however. Okay, sorry.
So we have here. Sorry, my video is not working because they tell me that the bandwidth is.
Okay. I will tell you what is here. So this is the ratio between the best value found by the deepest network with respect to the best value found by the shallow network. So if this ratio is 1, means that we have found the same value, okay, of the objective function. Remember that the problem, see, both in the objective and in the test error. If it's different from 1, we can have greater than 1, and the greater is with respect to 1, and the more the fact that you are using a deep network deteriorates your solution, let's say. And so this means that being greater than 1 is not nice. And if you look here, the difference is that with the pure incremental gradient, this is up to 60 seconds, so up to the best value found, yes, on the 10 runs. So the incremental gradient seems to be always worse with respect to the
suffering
for this. Yes, suffering for this. I mean, this is something that I am expecting. Sorry, Manuel, there is a small delay in the audio, so I'm sorry, I'm speaking over you.
Sorry for that. So what I was wondering is that this is a 10-fold difference in the number of variables, right? So 10-fold more variables than in the shallow networks, right?
Yeah.
Still, the test error is not dramatically decreasing. The test error.
But
so
you don't see here. But for looking to this, we need to check, for example, perhaps here. Yes, you can see here. Yes, the test error is dramatically going down here.
Ah, yes, here. Okay. Yeah.
This is
now
the
I understand the factor. Yeah, this is.
And here is also the objective function. Nevertheless, is dramatically. Let's say yes, dramatically, because these are very small numbers, 10 to the power of 2 less.
It's better.
So dramatically, it's better. So this is actually what it's proving, in my opinion, is that it's not always true that improving the training error will lead to overfitting. This is what is
the point I wanted to make. Yeah.
Okay, and also I need to mention, I didn't tell this. Of course, before doing these results, we made a k-fold cross-validation to find the best parameters that gives the best training and the best test error, so the best trade-off, as usual in machine learning. So then we run with these parameters, we run the optimization, and we make this comparison. But before, we put the setting for each of the problem, we put the setting of the network in a way that, sorry, the setting of, because there are some other hyperparameters which are not mentioned here, which is the sigma, for example, in the activation function and so on. And so we make some k-fold cross-validation for finding the best setting for the problem, for each of for the network in relationship with the problem. And then we make these results. So I was also surprising for this. I was expecting that improving so much the objective function, that was something that we want to examine, because, as I told you, we were motivated by the deep network, but this is a general framework. You have a sum of function, and you are decomposing also with respect to the variable. Can we prove convergence, and what happens to the behavior? Then we try on this, because this was the more natural stuff. We have not tried a more general optimization problem. But what I was expecting is that if I'm improving too much the objective function here, I will deteriorate the test error, because I'm going in overfitting. And actually this does not happen. I should also say that we stop here after 60 seconds. After 60 seconds, so we are not reaching, because of course here you don't have any chance to check if you reach optimality. And you also, I don't report it here, we also, at the very end, after stopping, we are evaluating the gradient of both the two, and it happens that our method find the norm of the gradient was less rather than in the incremental gradient method. And we try to use a clever update rule for the step size in the incremental gradient. We use the same for us. We, of course, I mean, it's not the best incremental gradient that you can find, but I mean, it was difficult to use the best incremental gradient method within our framework, because it's not possible to use the block stuff. So we need to implement by from scratch our one. So we try to do our best to make very good implementation for the incremental gradient here. But this is what I see here. That what is claimed that is always worse to find very small value of the objective function is not always true. Now there is someone
this is very good news for our community, because this is always the killer argument of the machine learning people. So
of course.
It's very good news to see that it's not true.
Then we need to use it in truly machine learning stuff. For the moment, we just make some optimization observation. So let's see what happens. Yes, I also feel that is good news. You're welcome, Manuel.
Thank you, Emmanuel, and thank you, Laura. It has been very interesting from, as you say, from the general optimization point of view to see different ways of building these decompositions. And also from the deep network point of view to see how powerful these decomposition techniques are. We are grateful to have had you here today, and we hope to see the audience back next week at the next seminar. Thank you so much, everybody.
I'm thanking you again, all of you, for this nice invitation. Very nice stuff. Thank you, Emilio, Dolores, and Cristina. Is it?
Yep. Thank you very much, Laura.